This lesson is about hydrogen bonds. Hydrogen bonds are intermolecular bonds. Intermolecular bonds. Inter means between. So hydrogen bonds are bonds between molecules, not within a single molecule. Bonds between molecules. Hydrogen bonds are strong dipole interactions, which means that the molecules involved in hydrogen bonding are highly polarized molecules. So we'll write that down. Strong dipole interactions, and the molecules which form the hydrogen bonds are highly polarized. But let's start at the beginning. Why do bonds form in the first place? Bonds form because positive and negative electrostatic forces attract. So it's the difference in charges which is the first step in forming hydrogen bonds. And let's look at an illustration. So these circles, each circle represents a molecule. And if we were going to form hydrogen bonds between these molecules, how would we draw it? Would we draw the bonds inside the molecule, or would we draw the bonds between the molecule? It would be something like this. So notice that the bonds I'm drawing are between the different molecules. I'm not going to draw every bond, but the idea is to understand generally how hydrogen bonds form. So if you notice that the bonds are forming between each molecule, so we call that intermolecular bonding. So let's switch to a more specific example using water molecules. So if we had hydrogen bonds forming, which they would, within this lattice work of water molecules. In this example, it would be most likely, because the molecules are highly organized, it would be crystallized water or ice, and hydrogen bonds would form. So how would they form? What would it look like? Would they form from hydrogen to hydrogen? Well, we said that the bonds form between molecules, not between the atoms within the molecule. So it would not form like this. How about between the hydrogen and the oxygen? Now, between the hydrogen and the oxygen, a covalent bond has formed, but it would not be a hydrogen bond. So this is not where the bond would form. So that is not how it would work. How about between the hydrogen of this molecule and between the hydrogen of this molecule. The problem is the individuals, the charges have to be opposite in order to attract. And those are between different molecules, but they do not have opposing charges. So this is not the way it would work. So let's go backwards. And let's add our partial charges. So now we see what charges we're working with. Notice that the hydrogen has a partial, the delta means partial charge, it's positive, and the oxygen has a negative partial charge. So the dipole moment within this molecule is positive at the hydrogens and negative at the oxygen. And in the next molecule, looking at the lower right, we have a positive, partially positive hydrogen, and it would bond with the oxygen at the lone pair, and the bond would look something like this. The next bond that we would see that could form would be the hydrogen forming with the oxygen like that. And notice that the partially negative charge and the partially positive charge are forming a hydrogen bond. That would continue throughout the lattice. Now notice we're working with one central molecule here. We would form a hydrogen bond here at the lone pair with the hydrogen, and then this lone pair. Notice that we have 4 hydrogen bonds forming in the crystal ice. If this was liquid water, because the shapes would be a little more squished and it would be a little more chaotic, we would have probably a maximum of 3 bonds that would form rather than 4. But because this is highly structured lattice work, we have 4 bonds forming per molecule. So this molecule is forming a bond, another bond with this hydrogen, and we're going to finish off all of our bonds here. So the bonds that would form would look something like this. And notice that the bonds are only forming between different molecules, and that it's the partial charge, partial charges are attracting each other. Let's look at another example using oxygen and hydrogen. This is methanol. So in this methanol illustration, hydrogen bonds are going to form. So I'm going to be devil's advocate again. Will hydrogen bonds form between this hydrogen and this hydrogen? So will we have bonds forming between these two molecules? No, they will not form that way. Even though they're different molecules, those are not, they do not have partial charges. We do not have a dipole moment at that location, so there is not going to be an attraction. Will there be an attraction? Will there be a hydrogen bond between the oxygen and the hydrogen? There is a covalent bond, but that will not be a hydrogen bond. So we'll back up. So let's form the bonds between the oxygen and the hydrogen. But in order to do that, we need to know where are the partial charges. So the location of the partial charges are now visible. So notice that we have, because this is methanol, we have an oxygen attached to a hydrogen, and the oxygen is highly electronegative. It's pulling the electrons from the hydrogen. So we have two partial charges. So this lone pair will be attracted to this hydrogen, will form a bond, and this hydrogen will be attracted to this lone pair. Notice that we have partial negative charge on the oxygen and a partial positive charge on the hydrogen, likely here. Here we have an oxygen and a hydrogen, hydrogen and oxygen. And notice that the hydrogen bonds are only forming where there are partial charges. Something like that. So that gives you a general idea of how the bonds would form. Now, I want to talk about why the bonds are forming on these particular elements. Why oxygen? Now, what we know is that bonds will form between hydrogen and fluorine, oxygen, or nitrogen. And the reason is that fluorine, oxygen, and nitrogen are all highly electronegative. And when they form a bond with hydrogen, they pull the electron from the hydrogen, become more negative, and the hydrogen becomes more positive. So that difference is what causes the charge separation. And I know what you're thinking. You're thinking, well, why doesn't that happen with the carbon? It doesn't happen with the carbon because I'm going to put a little table up here. Because with carbon, nitrogen, oxygen, and fluorine, the electronegativity difference between hydrogen and carbon is only 0.35. The difference between hydrogen and nitrogen is 0.84. So the nitrogen is really going to hold on to those electrons in this example. With the carbon, the hydrogen and the carbon are very close. So it's not going to be a highly polarized bond. With the oxygen, the electronegativity difference is 1.24. So it's highly polar bond. And then the fluorine is 1.78. So notice as we go left to right in period 2 on the periodic table, the atomic element is getting, the atom is getting smaller. It's becoming more electronegative in the outer part of the atom because the distance between the central proton and the outer valence electrons is becoming smaller and smaller. So there's a greater attractive force. So let's sum up what we've learned. So what we've learned is that Hydrogen bonds are intermolecular bonds. Hydrogen bonds take place between polarized molecules. A hydrogen bond is a strong dipole-dipole interaction between molecules. Molecules that form hydrogen bonds are hydrogen bonded with fluorine, oxygen, or nitrogen because they form polar covalent bonds. And the reason that the bonds are polar covalent is because the hydrogen atom is very small. It can actually get very close to the opposing molecule. And as we just said, the fluorine, oxygen, and the nitrogen are very electronegative. So the combination of the close interaction of hydrogen with the charge separation between the hydrogen and the fluorine, oxygen, and nitrogen are what creates those highly polarized molecules that want to form hydrogen bonds. I hope you enjoyed this. I actually really enjoyed making this video, and I hope to see you in future videos. Thank you.